Already we have seen the first order perturbation theory, that is a time independent stationary perturbation, particularly for a non-degenerate case. Now we will see the second order perturbation theory for a stationary state and non-degenerate case. In the case of first order perturbation theory, we have seen we have written the eigenvalue equation h psi, which is equal to E psi, in terms of lambda parameter. The reason for introducing lambda parameter, I have already explained in my earlier lecture, that the first order perturbation theory. So the Hamiltonian can be written into two parts. One is unperturbed Hamiltonian H naught. The other one is perturbed Hamiltonian H prime with lambda parameter. The reason already I have explained it. So here lambda 0 means unperturbed system. Lambda is 1 means maximum perturbed. Similarly, the wave function can be written in the power series of lambda. This also I have already explained in the first order perturbation theory. That is, psi can be written as psi naught, that is unperturbed wave function, plus lambda psi 1 first order perturbation, plus lambda squared psi 2, and it goes on. Since lambda is very small, we have ignored higher order term. Similarly, in the right hand side, E psi, here E naught is unperturbed energy eigenvalue, plus lambda E1 plus lambda squared E2, it will, goes on. This is first order energy correction, this is second order energy correction. Similarly, the wave function can be written as psi naught plus lambda psi 1 plus lambda squared psi 2, and it goes on. Now, as in the case of first order perturbation theory, you can compare the second order lambda power lambda power 2, that is second order in lambda. So, in order to find the second order perturbation, you equate the terms both side lambda squared terms. So, if you equate the lambda squared term, just you go through this left hand side, here h naught, here in the bracket, third term is lambda squared term. So, h naught psi 2 here, h naught psi 2. That's what I have written here. Similarly, other lambda squared term, here you have lambda, here one lambda, second term. So if you multiply, you will get the lambda squared. That means h prime psi 1 is a lambda squared term. That is a second order in lambda. These two terms are second order in lambda. Similarly, you look into the right hand side. Here E naught, you multiply with lambda squared psi 2. So E naught psi 2 you will get. Similarly, if you multiply lambda E1 with lambda psi 1, you will get lambda squared. So that is E1 psi 1. Similarly, the lambda squared E2 is here. So here psi naught without lambda. So lambda, if you multiply E2 and psi naught, you will get lambda squared term. So you are equating this. That is second order in lambda. You are equating the left hand side as well as right hand side, the second order in lambda. So here you bring the energy state psi 2 in the left hand side. Here you have H naught psi 2. Here you have E naught psi 2. So you bring E naught psi 2 to the left hand side. So this will become minus E naught psi 2. So that's what I have written here. And you bring this H prime psi 1 term to the right hand side. So now you will get this E1 minus H prime psi 1 this term. psi 1 you are equating psi 1 and of course E2 psi naught. Now, what you are going to do is, as you have done in the case of first order perturbation theory, you take an inner product with the psi naught because psi naught is the unperturbed wave function. So, if you take the inner product of psi naught, this left hand side will become psi naught, bra psi naught, h naught minus e naught into get psi 2. Similarly, in the right hand side here, you have psi 1, get psi 1, so bra psi naught. Similarly, here you have get psi naught, you have bra psi naught. So, after taking inner product with the psi naught, you got this expression. Here, some interesting thing we can see. You first take the left hand side. When H naught act on psi 2, you will get the energy eigenvalue E2 because it's a unperturbed Hamiltonian, which is a number. So you can take this outside because it's a number. E2 minus E naught is a number. So then it will become the inner product of psi naught with the psi 2, which will be equal to 0 due to orthonormality condition. The inner product of psi naught with the psi 2 is 0. So the left hand term will get cancelled. This will become 0. That's what I have written. About the right hand side, now you come to right hand side. This I can write psi naught E1 psi 1 and minus psi naught H prime psi 1. And of course, this is since E naught is a number, I can take sorry, E2 is a number, eigenvalue I can take out. So it will become inner product psi with psi naught with psi naught. So psi naught with psi naught is equal to 1. This is equal to 1. So simply you will get E2 here. And what about this term? Here you have E1. If you take E1 outside, then inner product of psi naught with the psi 1 will become 0 due to orthonormality condition. So this will become 0. So naturally here you have E2. Here you have minus that I will use different color. Here you will have minus psi naught H prime psi 1. So you don't know what will happen if H prime act on psi 1 because it's a perturbed Hamiltonian. So naturally E2, if you bring this to right hand side, E2 will be equal to, this will become plus psi naught H prime psi 1. This is the equation. Now what we are going to do is, as done in the case of first order perturbation, psi naught is the initial wave function that we have taken um. Uh, in the form of Dirac notation, um can be written simply bra m because this is bra psi naught. So that can be written as initial value can be written as bra m. And H prime, this psi 1 can be written as summation over n of 1 into get n. That is I have shown in the red color box. That is I have expanded psi 1 in terms of un. Un in terms of Dirac notation can be written as get n. So this is we have used that superposition principle. So we have expanded psi 1 as a summation over an of 1 into get n. So that's what we have done here. Now we will see what will happen to this. So we got E2 is equal to summation over an of 1 into m h prime n. Uh, from the first order perturbation theory, we have seen an of 1 is equal to n h prime m over en minus em, where em is the initial energy state uh, initial energy eigenvalue, En is final energy eigenvalue. So you just substitute, replace n upon pi this one, n h prime m over En minus Em. And of course, you have m h prime n. Here, h prime assumed to be Hermitian. If it is Hermitian, then only we can interchange pra and get vector. So now I am interchanging the pra and get vector. That is n and m is interchanged. So this will become m h prime n multiplied by m h prime n. Now you can see, if you carefully analyze this, you will get m h prime n modulus squared. That is this thing whole square. Modulus of m h prime n whole square. And remember that in this case, n is the final energy, m is the initial energy. Here we are interchanging vector and get vector. So naturally we are interchanging the initial energy and the final energy. Instead of En minus Em, I am replacing Em minus En. And also here in the n is not equal to m. So that is more important. So you will get the summation over n, which is not equal to m. You will get m h prime n whole square over em minus en. If n is equal to m, then naturally this will go to infinite, which is not an acceptable solution. So n is not equal to m. That also we have seen in the first order perturbation theory. So we will see what will happen. Now we found E2 is equal to summation over modulus m h prime n whole squared over em minus en. We will see further. So E2 is equal to summation over uh, modulus of m h prime n whole squared over em minus en. Where n is not equal to m. This is the second order energy correction. This is the fundamental result of second order perturbation theory. We have seen for the first order perturbation correction E1, the energy correction in E1 is equal to psi naught h prime psi naught. This is exactly equal to the expectation value of uh, perturbed Hamiltonian under unperturbed wave function. That is more important. Psi naught is the unperturbed wave function. So this is naturally the expectation value of the perturbed Hamiltonian under unperturbed energy state, that is unperturbed wave function. You can see this is a very simple expression. Simply is a expectation value. But here you can see it is little bit complicated. Second order perturbation is complicated comparing the first order perturbation. And further, our ultimate aim is we want to find the expansion coefficient. The reason being is only if you know the expansion coefficient, then you can calculate the probability. As I said, now our aim is to find the expansion coefficient of second order perturbation. At the beginning of our my lecture, we have seen by comparing the second order in lambda, both left hand side and right hand side, we got this expression. Remember that we got h naught minus e naught into psi 2 is equal to E1 minus h prime psi 1 plus E2 psi 2. Now we will see what will happen if we take the expansion of this psi 2 and psi 1. So actually we got this expression by comparing the lambda squared value. Coefficient of lambda squared, that is h naught minus e naught into psi 2 is equal to E1 minus H prime psi 1 plus E2 psi naught. Now, psi 2 can be written in the expansion form that summation over an of 2. Remember that in the case of first order perturbation, we have mentioned this as an of 1. Here it is a second order correction. So we are using an of 2 into un when n is not equal to m. So this is our expansion. So you substitute this here. In the left hand side, you substitute the side 2 as a summation over an of 2 un. For side 2, I have substituted this, which I have shown in the red color circle. That is, psi 2 is replaced by summation over an of 2 into un, as shown here. Similarly, psi 1, using the same method, same procedure, and also we have done it in the case of first order perturbation theory. This psi 1 can be written as summation over an of 1 un. So we have expanded this psi 1 and psi 2. Of course, this is the unperturbed wave function. So that is initial wave function which we have taken as um. So this can be written as e to um. So now you can rewrite this. What will happen when H start act on un? You will get a energy eigenvalue of En because this is unperturbed Hamiltonian. When unperturbed Hamiltonian act on un, you will get energy eigenvalue En. That is a well-known fact. So this will become an2 En minus Em into un. This is about left hand side. Regarding the right hand side, what will happen? Uh, you don't know what will happen when H prime act on un because it's a perturbed Hamiltonian. Now what I am going to do is you take a inner product with UK. So what will happen if we take inner product? See here, En minus Em is just a number. An also a number. You can take out from the inner product. So this will simply become Kn. Uh, from Dirac notation, you can understand this is UK, this is UN. So in the form of Dirac notation, this can be simply written as inner product of K with N. So same thing here. See, here you can take inner product. You can expand this. You can take E1 outside because E1 is a number. You can take it out. So this will become bra K into Kn minus this K uh, because we are taking inner product with the K H prime N, the second one. That is this one. H prime un because we don't know what will happen when H prime act on un. So we are taking that as it is. That is K H prime n. Then if you take inner product, E2 is a number you can take out of the inner product. So this will become inner product of K with M. You know very well that due to orthonormal property, this will become 0. That is inner product of K with M will become 0. So this term will go away. This will go away. So only remaining term will be left out. We will see what will happen to those term also. So finally we arrived with this expression. Now we will see some interesting phenomena about this. First you take left hand side. Left hand side, when if you take inner product of K with N, what will happen? Naturally, due to orthonormal property, this circle I have shown in the circle, uh, blue color circle, this inner product will be 1 only if n is equal to k. So what I'm going to do is I will replace an up to pi ak up to. Similarly, en as ek, because the summation exists only for one value, that is when n is equal to k. So I have replaced the n by k. For all other term, it will be 0. So summation will automatically get eliminated. Only for one value, when n is equal to k, this term exists. So I have written this as ak2 into ek minus em, which is equal to, now we will come to the right hand side. What will happen? When you take right hand side, E1 I have taken outside. So Kn, same principle. If you apply, the summation exists only when n is equal to k. So for all other value, it will be 0. So here summation is meaningless. There is only one term, that is ak1. AK1 into E1, because for all other value of n, this term will become 0. So only a non-zero term is AK of 1 into E1. Similarly, the second one, because I have separated this into two parts, that is in the square bracket. There is a square bracket here. I have separated this into two summation. So next, what will happen to the second one? So here also an of 1 will come. Of course, minus. There is a minus sign. An of 1 k h prime n. As we are discussing already, we don't know what will happen when perturbed Hamiltonian act on the Kettian. So we are leaving this as it is. So finally, in the left hand side, first term will become ak1, ak of 1 e1 minus this term when n is not equal to m. So this is our final expression. We will see further what will happen if we simplify it further. So finally, we arrived with this expression. Here we know the AK1 from first order perturbation theory, AK of 1 is equal to K H prime M, that is pra K H prime get M over EK minus EM. And also we know E1 energy correction, first order energy correction is psi naught H prime psi naught. We know the psi naught is initial unperturbed wave function, which is equal to UM. In Dirac notation, it can be written simply as bra M and get M. That's what I have done it here. You substitute this here. For ak of 1, you substitute this one. That is a k h prime m over ek minus em. E1 is m h prime m. So similarly, an of 1 can be written as using this formula. That is here k is replaced by n, because here ak upon here an upon. So naturally this k will become n. So this will become n h prime m uh, over en minus em into k h prime n. This is the our final expression. Here, our ultimate aim is we have to find AK of 2. So naturally, you have to bring this EK minus EM to the right hand side. So if you bring to the right hand side, in the first term, what will happen? EK minus EM. Here also one EK minus EM. This will become EK minus EM whole square. Similarly, in the second one, there is En minus Em here. If you bring this Ek minus Em, this will become like this, Ek minus Em. This is the coefficient for second order correction. If you take the square of this, you will get a probability. See, Here you can really visualize how complicated it is. The coefficient, second order perturbation coefficient is this much. So much complicated. You can see the first order coefficient, first order perturbation coefficient, how simple it is and how complicated it is. If you go for third order and fourth order, it will get to more complicated. And as I said, since lambda value is very small, you can ignore the higher order lambdas of higher order. So this is about the second order energy correction and the second order expansion coefficient. Thank you very much for watching my video and supporting me continuously.